So we will begin with what we call the basic counting principle. Okay? And we're just going to find out how many ways something can happen. Now, if we know that the one thing can happen m different ways, and then after this there's another event that can happen n different ways, then the number of ways the two events can occur together is m times n. It's a very basic idea. What do I mean by that? Okay, I'm going to get 3 dice, roll them. And that's a common sort of probability question we see. You know, how many 6s do we get and things like that. How many ways can it happen? And then I think, okay, well, first of all, I'm going to have 1 dice. Because whether I roll them one at a time or all 3 together really doesn't matter. Because all I'm looking at is the final outcome. So the first dice, well, there's 6 different ways it can happen. It can be a 1, 2, 3, 4, 5, or 6. Same with the second one. Same with the third one. So using the basic counting idea, total number of possibilities would be 6 times 6 times 6. If I was to draw up the tree diagram, we would see that. The first dice would branch off 6 ways. Then each of those would branch off another 6 ways. And then each one of those would branch off another 6 ways. That's going to be a huge tree diagram. We'd end up with 216 branches. Now, if all I'm interested in is what's the probability of rolling 3 6s, I don't need that huge tree diagram because I know of all those 216 ways the dice are rolled, only one of those outcomes is going to be 3 6s. So I know the probability is 1 in 216. So, well, same number. I said all 6s, but let's just say all the same number. How do I work that out then? Okay, I'm going to roll the first one. The first one, again, has 6 different numbers that the first one can have. But once I've rolled that first one, because I want all of them to show the same number, there's now only one possibility for the second die. It's got to be the same number. And then there's only one possibility for the third die. It's got to be the same number. And so there are 6 ways. And if you think about that logically, that makes sense. They could all be 1s, or they could all be 2s, or they could all be 3s, or they could be... There's 6 different ways. Which brings up then the logical question, what's the probability that all 3 dice show the same number? Well, 6 out of the total number of possibilities, 216, which I think simplifies down. 1 in 36 chance of that happening. 1996 HSC question. They got these mice. Placed them in a maze. The maze has 5 exits. Each mouse is equally likely to leave the maze through any of the 5 exits. Thus, the probability of any mouse leaving a particular exit then is 1 in 5. There's 1 in 5 chance. There's 4 mice conveniently named A, B, C, and D. Don't know how they came up with those names, but there you go. They're put in the maze and they behave independently. So all that means is what one mouse does doesn't affect what the second mouse does, and so on. What's the probability that A, B, C, and D all come out the same exit? Now, I'm going to use the basic counting principle, but I'm using probabilities this time rather than number of outcomes. So probability they all use the same exit. Well, I'm saying, well, the first mouse can go through any door because it would now dictate how the others are going to behave. So there's a probability of 1 that it leaves. It's definitely going to go. So it has to happen. It's a certain event. But then the second mouse, what's the probability that that mouse goes through the same exit? Well, now there's only a 1 in 5 chance that it goes through the same as that first mouse. And then the next mouse, there's a 1 in 5 chance that it goes through the first one. And then the next mouse has got a 1 in 5 chance. And so all up, we have a 1 in 125 chance that they all go through the same exit. I could have done that via the basic counting principle. I could have first of all said, how many different outcomes are there? Well, that would be 5 times 5 times 5 times 5, because each mouse has 5. And then how many ways do they go through the same exit? Well, the first mouse has 5 to go through, but then the second one would be 1 times 1 times 1. So you have 5 over 5 times 5 times 5 times. Turns out to be the same answer, 1 in 125. All right, so this is a little bit more interesting. What is the probability that A, B, and C come out the same exit, but D goes out through a different one? I'm going to have D go out first. So D can go through any door. It's the first one to leave. Doesn't matter. Out it goes. Probability of 1 of that happening. So along comes the next mouse. And it now just can't go through the same one as D. But it's got 4 to choose from. So 4 and 5. But then the next mouse, or the next 2 mice for that matter, has a probability of 1 in 5 because it's got to go through the same door as the second mouse. And so we get 1 times 4/5 times 1/5 times 1/5. We get a probability of 4 in 125. What is the probability that any of the 3 mice come out the same exit and the other mouse comes out a different exit? Well, the last question we just did was what was the probability that A, B and C went through the same one and D went through? And we worked out that that had a probability of 4 in 125. But at the end of the day, D is just a letter. So I could have done the same question with A and said, well, what's the probability that A uses a different exit to the other 3? That would also be 4 in 125. What's the probability that B uses a different one? That'll also be 4 in 125. What's the probability that C goes through a different one and A, B and D the same? Also 4 in 125. So all up, the probability that any mouse uses a different exit to the other 3 would be 4 lots of 4 on 125. And we have 16 on 125. So what is the probability that no more than 2 mice come out the same exit? No more than 2 come out the same exit. I'm going to use an idea that we use a lot in probability, and it's what's called the complementary event. Sometimes it's easier to work out the other situation. And all probability must add up to 1. So then I just subtract that answer from 1, and I've got the answer. So instead of working out no more than 2, I'm going to say it's 1 minus the other situations. Well, what's the other situation? If it's no more than 2, the other situation would be more than 2. In other words, 3 use the same exit, or 4 use the same exit. The reason I'm solving it that way, we've already worked those out. So remember, the first question we had was they all use the same one, and then the last one we just looked at was probability that 3 use the same one. So using the complementary idea, I can get that answer quite quickly. All right, so that is, I guess, the first way we count ideas. The next thing we look at is what's called a permutation. And what is a permutation? Okay. All it simply is an ordered set of objects. So the actual order things happen in is important. Okay. So me walking through the door before the class would be different to the class walking in before me. Yes, we end up with the same effect. We're all in the same room, but how we got in there was different. So the actual order is important. Break it down into cases. We're going to have n different objects, and we're going to select all n of them. How many ways can we select these n objects? Okay, so I'm going to use everything. I'm going to use every object. So I've got n different objects. I'm just going to arrange them in a line out the front of the room here. They're in the corner over there. Yes, I love the way some people actually looked. Okay, so imagine they're over there in the corner. And we're going to arrange them. So what we do is we say, okay, look, guys, I'm going to arrange you in front of this room. Who wants to be first? Okay. Well, there's n different choices I've got for that first object. So they finally worked out who it's going to be. There was n different ways I could have done that. Now I'm going to go, okay, I need the next person. Well, now there's n minus 1 ways I could choose. And then the next person, n minus 2. And so on and so on. So it's still the basic counting idea. How many ways can I do the event? And I would keep going, but I'm using all the objects. So eventually I'll get to a point where there's just 1 left in the corner, and we end up with n times n minus 1 times n minus 2, all the way down to 1. Well, in maths, we have a notation for that you may recall, n factorial. N factorial. So if you want to arrange n objects, the number of ways you can do it, n factorial. So let's look at some of these questions. 5 boys, 4 girls, arranged in a line. How many ways can I do it? There's no restrictions on this problem. Well, if there's no restrictions, the fact that I've said 5 boys and 4 girls is irrelevant. I may as well just said 9 people. There's no restrictions as to how they come up. So there's 9 factorial ways of doing it. I'm going to arrange 9 people, okay? No restrictions, gender doesn't matter. And for interest's sake, there it is, 362,880. Let's put a condition on it because they're much more fun when we put a condition on it. The boys and the girls alternate. Here's how I deal with it. I look after the condition first. Now, is there a condition on this problem? Is there a way I must start the line? Has to be a boy. Right? Otherwise, I will run out of girls. So if I start with a girl, I'm going to go girl, boy, girl, boy, girl, boy, girl, boy. Oops. I haven't got any girls left. So there is actually a condition here. Always look after these conditions first. So I only have one choice for that first person. It has to be a boy. Now I'm going to go and arrange the boys. Fellas, just go line up, will you? 5 factorial ways they can do that. Now the girls. Girls, sort out the order you want to be in, but just slot in between the guys, will you? 4 factorial. Most people probably wouldn't worry about the 1. The only time you need to worry about that is, say I had 4 boys and 4 girls to arrange. Then there would be 2 ways I could start the line. And so I'd go 2 times 4 factorial times 4 factorial, because the first choice would be, how am I going to start this line? What's the probability? Here's the logical next question. Well, what's the probability we get you to line up and you all decide to make the line look pretty and go, white shirt, yellow shirt, white shirt, yellow shirt. Well, then it must be 2,880 out of 362,880, which is 1 in 126 chance of that happening. But as always happens, okay, so that's now the condition on our problem. We're no longer worrying about alternating. We're just looking after these 2 that wish to be together. So you say, okay, how many ways can these 2 people be together? Well, now it's a group of 2 people. So there's 2 factorial ways of arranging those 2 people. But now, once they've decided this is the order we're going to be, they're like one object now. They're one person. They've got to stay in that order. So the question now becomes, how many ways can we arrange 8 objects? Our 2 girls that wanted to be together is one object, and then there's 7 other who really don't care. So all up, 8 objects to arrange, 8 factorial. So we get 2 factorial, 8 factorial, 80,640 ways of doing that. So that's if we use all the objects. What happens if we don't want to use all the objects? Some people get left behind in the corner over there. So we're only going to use some of the objects. That's why we're saying k is less than n. Number we use is going to be less than all the objects. We're going to start the same way. N objects over in the corner. Going to line you up. Who wants to be first? But there's still n ways. Then the second person, come on, we're going to form this line. N minus 1. Yep, next person, come on. N minus 2. We're going to keep going until we get to the kth person. How many ways of arranging or selecting the kth person? And look at it carefully. There were n ways of choosing the first person. There were n minus 1 ways for the second person. There were n minus 2 ways for the third person. So for the kth person, there would be plus 1. N minus k plus 1. Well, geez, that's a bit of a bother to remember. There's an easier way of remembering this. I'm going to multiply top and bottom by all the people we left behind. The number of ways we could have arranged. We chose not to use them. But if I had, then I would have gone n minus k minus 1 all the way down to 1. And I'll multiply top and bottom by that. But by doing that, look what happens. On the top of the fraction, I get n factorial. On the bottom of the fraction, I get n minus k factorial. That's a lot neater to remember. So n factorial on n minus k factorial, which is what we call npk. And on your calculator, you will have a button that will evaluate npk. I think on some it's on the division symbol, and you have to press function first or something like that. but somewhere on your calculator you should find a button that will work out, NPK. That doesn't mean don't remember the definition, because sometimes problems might involve algebra rather than numbers, so you still got to know the actual definition. But the way I think of remembering it is the number of ways I could arrange all of them divided by the number of ways I could arrange the ones I didn't use. I didn't use n minus k of them. So I'm dividing by the number of ways I didn't use. Okay, time for an English lesson. Letters of the word problems. How many 5-letter words are possible? But the beauty about English in a maths lesson is, as far as we're concerned, everything is a word. Blems is a word. Smleb is a word. Robble is a word. Blur is a word. There's just 5 letters, it's a word. No restrictions, because this is maths. We don't worry about grammar for this anyway. Okay, 8p5. I've got 8 letters, but I'm only going to arrange 5 of them. So 8p5. Now, if you don't have a calculator, it is 6,720, but the way you would work it out is you'd say, well, that's 8 factorial over 3 factorial. There were 3 letters I didn't use, which would go 8 times 7 times 6 times 5 times 4. And as I say, if you don't have your calculator, but you're very clever, you will come up with 6,720. Let's make the word more interesting. The word has to begin with P. Look after the restriction first. The restriction is it has to begin with P. How many ways can it begin with P? 1. It wasn't a trick question. There's only one way, and that is begin with P. So, all right. I've put P in the problem. There's one way I could do it. So now what is the question? I still got 5-letter words. There's 4 letters left to go. But the question now becomes equivalently, I've used P, how many 4-letter words from problems? So I've got 7 letters left. I'm going to use 4 of them. So 7p4. And 7p4 is 840. Let's make it even more interesting. P's included. Okay, we're going to use P because we like P, great letter. But this time it's not going to be at the beginning. But M has been bad. No, M's not in our word. It's excluded. Look after the condition. P is included. Okay, well, let's do that. How many ways can I include P in my 5-letter word? But not at the beginning. So there's only 4 ways because it can't go in the first spot. So P is included, but not at the beginning. 4 ways I can put P into the problem. Now, M is excluded. Can't use that letter. So now it's 6p4 because I've used P, not allowed to use M. So the question now is 4-letter words from Robbles. 6p4. 6p4. 1,440 ways of doing that. Right, we're in a boat. 6 people, in fact, are in a boat. They've got 8 seats. 4 creatively spelt on each side. Oops. Okay, like I said, this is maths, not English. What is the probability that Bill and Ted are on the left side and Greg's on the right-hand side? Okay. If I want to work out a probability, bottom of the fractions, total number of possibilities with no restrictions. So I work that out first. There are 8 seats in my boat. I'm going to use 6 of them. So there are 8p6 ways I can put people in my boat. So the bottom of the fraction will be 20,160. So no restrictions. Now let's do it with restrictions. Bill and Ted are on the left side. Well, that's going to become 4p2 because there's only 4 seats on the left side and Bill and Ted are going to use 2 of them. So 4p2. Greg's come along and said, well, if they're going on the left side, I'm going on the right. 4p1. There's 4 seats. Going to use 1 of them. The rest of the people are going, you guys are idiots. What's the matter where you sit? So now, how many seats are left? 5. How many are we going to use? 3. So we end up with 5p3. That's the way the rest can go in our boats. And that turns out to be 2,880. So the probability of Bill and Ted being on the left and Greg being on the right is 2,880 out of 20,160. 1 in 7 chance. 1 in 7 chance of that happening. Another HSC question. A bit more recent. Sophia's got 5 coloured blocks. One is red, one's blue, one's green, one's yellow, one's white. She then stacks 2, 3, 4, 5 blocks on top of one another to form a tower. In other words, one block by itself is not considered a tower. It's just a block. But as soon as I put 2, it's now a tower. Okay. So we can have 2 block towers, 3 block towers, and so on. What's the question? Oh, how many different towers are there that she could form that are 3 blocks high? Well, I've got 5 blocks I can use. Because they're different colours, the way I arrange them will make the towers different. So it's a permutation. The order that I stack them is important. So 5, going to use 3 of them, 5p3, 60 different towers we could build that are using 3 blocks. Well, how many altogether? Oh, well, 2 block towers, 5p2, 20. 3 block towers, we just worked that out, 60. 4 block towers, 5p4, 120. 5 block towers, 5p5, which by the way is the same as 5 factorial because we're using all of them, also 120. Giving me a grand total of 320 different towers we could build. All right, that was a very long introduction. We're going to do 10E, not 39. Don't know why. Possibly because it's a multiple of 3, which is really big.